All right, so now we need to talk about naming compounds that have a transition metal. Okay, so we have an ionic compound. We have to figure out the charge on the metal with a Roman numeral. So I sort of mentioned this on Wednesday. We have FeCl2 versus FeCl3, and so obviously both compounds cannot be called iron chloride because they're completely different. They have different physical and chemical properties, and so you're having to specify the compound by giving an indication of oxidation number for the metal. So the way you do that is to basically, if you look at the formula, you can figure out the charge on the iron by balancing the charges, sort of like we did before. So we know that chlorine has a -1 charge because it's a halogen. And so if we go back and look at our periodic table here, chlorine is a halogen. It has -1 charge. So it is going to have to be balanced out by, let me see, by the metal. So let's see. Here we go. All right, so here if chlorine has -1 charge, and there's two of them, so it's -2 charge overall. Because there's only one iron atom here, iron has to be +2. So for iron 3 chloride, it's iron 3 because, again, chlorine, each atom has -1 charge. Overall, 3 times -1 is -3. So iron has to be +3 because there's one iron atom here. And so the name for FeCl3 would be iron 3 chloride. Okay, what about this next formula here? Cr2s3. So Cr is chromium, S is sulfur. So we don't know the charge on chromium, but we do know the charge on sulfur. So we can figure out the charge on chromium by doing a little bit of math. So sulfur, remember, sulfur has a -2 charge. If we look that up on the periodic table, let me get rid of this here. Sulfur has a -2 charge, right? It's in the oxygen group here. So if sulfur has -2 charge, and -2 times 3 is -6. So chromium must be +6 overall, but it has 2 atoms of chromium, so it's going to be +3. Okay, because 6 divided by 2 is +3. So the charge on chromium is going to be +3. So the name is going to be chromium 3. Sulfur becomes sulfide. Now, you have to remember with Roman numerals that the charge that you write when you're writing the Roman numerals, it has to be the oxidation number for one atom of the metal. Okay, so notice here in our 2 previous examples, there was only one atom of iron. And so, of course, the charge was whatever the charge was on that atom. But in this case, this third example here, we have 2 atoms of chromium. So 2 atoms of the metal. And so we had to figure out the charge per atom. So we knew that chromium had to be +6 because sulfur was -6. But because there's 2 chromium atoms, 6 divided by 2 is +3. So the charge on each chromium atom is +3, so that's why it's chromium 3. Okay, it's not chromium 6 sulfide, it's chromium 3 sulfide. Okay, so most of the transition metals and some main group metals can form 2 or more cations with different charges. The charge of the metal ion is specified by a Roman numeral in parentheses after the name of the metal. All right, and so which elements are those? Well, here they're highlighted right here. Most of the elements sort of in what's called transition metals. These are elements that have multiple charges for their cations. All right, so we look at FeCl2 is iron 2 chloride, FeCl3 is iron 3 chloride. We already went through that. And so this next one, we're going to talk about Hg2O. So here mercury is a transition metal. If we look here, its location on the periodic table is right here. And so it can exist as different charges. Okay, so we have to use a little bit of math to figure out the charge on mercury oxide. So because we don't really know the charge on the metal, we know the charge on the nonmetal. If we look up oxygen, remember oxygen has a -2 charge, all right? And so if oxygen has a -2 charge, then mercury has to have a +1 or +2 charge overall, right? And so because there are 2 atoms here, so 2 divided by 2 is 1. So it must have, each atom of mercury must have a +1 charge. So the formula for Hg2O would be mercury 1 oxide. 1 because this is has a +1 charge for each atom of mercury. Okay, looking at this next one, SnF2. So Sn is 10, F is fluorine, or fluorine becomes fluoride. So the charge on fluorine is going to be, again, -1. It's a halogen. Okay, so fluorine's -1 per atom. There are 2 atoms there, so fluorine has to be, overall, it has to be -2, right? So I need a +2 here. So that must mean that because we only have 1 atom of 10, 10 must be +2. So the name for this compound would be 10 Roman numeral 2. That's the oxidation number, the charge on the metal here, +2. So 10(2). And then fluorine becomes fluoride. Okay, so fluoride. So 10(2) fluoride would be the name for that one. Okay, so what about SnF4? So SnF4, do the same process here. So SnF4. Again, fluorine has a -1 charge. There's 4 atoms of it, so -1 times 4 is a -4 overall. So 10 must be +4 here, for, remembering they have to add up to 0. So the name for this one would be 10 Roman numeral 4. Fluorine becomes fluoride. Okay, fluoride. So 10(4) fluoride. Okay, let's look at our textbook here for some more problems. So here we have several different compounds that we're having to name. And so at this point we can go to the first one, Fe2S3. Okay, so Fe2S3. So when I look up on the periodic table, where is Fe located? Okay, that's important because, if it's located in like group 1 or 2 or even 3, I should be able to predict the charge. But I know iron has multiple charges. I've used it before. I've named it before. So it's a transition metal, so that means I have to rely on the other element. The other element that was in the compound was sulfur. The sulfur has a -2 charge. Okay, so if sulfur has a -2 charge, 3 times -2 is -6. So iron must have to have a +6 charge overall to balance out the charges. All right, but notice there's more than 1 atom of iron. There's 2 of them. So 6 divided by 2 is 3. So iron must have a +3 charge there. So the name for this is going to be iron, Roman numeral 3. Sulfur becomes sulfide. Iron 3 sulfide. All right, so looking at the second example here, CuSe. So looking for the element Cu, that's copper. And so again, copper is a transition metal. And so then we have to look up the element Se, which is selenium. And so selenium has a -2 charge. We don't know what the charge is for this copper. So but we know selenium has a -2 charge. So copper must have a +2 charge. It's a 1-to-1 ratio there, so it's just going to be copper, Roman numeral 2, because that's its charge. Selenium becomes selenide. Okay, so copper 2 selenide. Okay, next compound here, GAN. So again, we're looking up the element Ga, which is gallium. Okay, so gallium is going to have, you notice whenever in your textbook there was a periodic table that showed the ions that were always had certain charges, like aluminum is always +3. Gallium is actually variable. Okay, so tin is too, and some of these other ones, lead and thallium. And so these are also variable, and so we have to figure out the charge on gallium by knowing the charge of the nonmetal. And in this case, we're talking about nitrogen, so its charge would be -3. And so if we have a -3 charge for nitrogen, gallium must be +3. So its name is going to be gallium. Nitrogen becomes nitride. Oops, I forgot to leave a space there. All right, so we also have to give it some sort of charge, right? So because the charge is a +3, this is going to be gallium, Roman numeral 3, nitride. Okay, gallium, Roman numeral 3, nitride. Okay, so when we're talking about molecular compounds, those are the ones, of course, where the atoms are sharing electrons, and they're formed by 2 atoms that are nonmetals, or an atom that's a nonmetal, another atom that's a metalloid. And so there's a different way to name molecular compounds. Okay, so we've talked about ionic compounds, how if they have 1 charge, and how to name those, and then if they have multiple charges, how to name those using a Roman numeral. And so now we need to talk about molecular compounds. So let me again show you this flowchart. It's very helpful. I would suggest you use it when you're starting to practice naming compounds, and then hopefully you can get to a point where you don't need to look at the flowchart as often. So we've talked about the rules for naming ionic compounds, and then now we need to talk about naming molecular compounds. The good news is that it's pretty easy compared to the ionic compounds. Molecular is a lot easier. So let's go ahead and jump to it. So the hard part about molecular, naming molecular compounds, is having to memorize the prefixes. Okay, so you can't get away from this, but I'm sure most of you are familiar with these prefixes anyways, because you've probably heard of a hexagon and a heptagon and an octagon and an nonagon, and that sort of thing in math. So prefixes mean the same here. So if you have 1 atom, it's referred to as mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 hepta, 8 octa, 9 nona, and 10 deca. Okay, so you have to memorize these prefixes again, or else it's going to be very difficult to name molecular compounds. Okay, so with molecular compounds, we're using different set of rules. The atoms are involved in covalent bonding, which is the sharing of electrons. There is a significant variation in the ratios of the atoms in a molecule, so you could have many atoms of one type of element bonded to a single atom of another. The names for the molecular compounds must explicitly identify these ratios. The name of the more metallic element, that's the one first to the left and or bottom of the periodic table, is named first, followed by the name of the more non-metallic element, with its ending changed to IDE. So the second element, its suffix changing to ID is just the same as that we're talking about naming ionic compounds. So the number of atoms of each element are designated by Greek prefixes, which we talked about just a moment ago. So a couple things to remember when naming molecular compounds. When only one atom of the first element is present, the prefix mono is usually not used. When two vowels are adjacent, the A in the Greek prefix is usually dropped. So I'm going to give you a couple examples of that. All right, so we said when only one atom of the first element is present, the prefix mono is usually not used. So here's an example of that. CO2. Okay, so there's only one atom of the first element here, carbon, and so we wouldn't write monocarbon. We would just call it carbon. And then there's two oxygen atoms, so 2, which is di. The prefix for 2 is di. And then oxygen becomes oxide. So you know you're very well and familiar with CO2 is carbon dioxide, right? It's one of the gases that we exhale. All right, so comparing that to C2O. So because our first element has more than one atom of it, so we're going to have to use the prefixes for that. Now, so 2 is di, so this is going to be dicarbon. And there's one oxygen atom here, so we have to indicate how many oxygen atoms there are. So monoxide. All right, so remember our prefix was mono, okay? And then oxide, right? So it's not going to be mono oxide. All right, so you notice I dropped an oxygen, or not an oxygen, an O, okay? I dropped the letter O. And sometimes, for that second rule here, sometimes it ends with an A, okay, and you drop a vowel. You don't want to have two vowels next to one another, okay? So monoxide is just one O, not two O's, okay? And so we're having to discuss that, and as we go through this, you will see these rules pop up every once in a while. All right, so let's talk about naming a molecular compound. So here we have SO2, so S is sulfur. Okay, there's one sulfur atom, so you don't have to use mono, and that's only true when it's the first element. The second element, there's one atom of it, you have to use the prefixes, okay? So you only do not have to use a prefix when it's the first atom and there's only, of course, one atom there. So S is sulfur, 2 is di, so oxygen becomes oxide, so this is sulfur dioxide. SO3, so S is sulfur again, 3 is, the prefix for 3 is tri, so O is oxygen, oxygen becomes oxide, so sulfur trioxide. Okay, next one, NO2. So here we have NO2. So one nitrogen atom, so it's just nitrogen for the first element. And the second element, there's two atoms of oxygen, so 2 is, prefix for 2 is di. Oxygen becomes oxide. Okay, so nitrogen dioxide. And notice you have two vowels here, okay, but so I and O, it's okay, but if it's O and A or O and O, that's when you're going to take off a vowel there. All right, N2O4, 2 nitrogen atoms, 2 is di, so dinitrogen. 4 is tetra, so here's an instance where we drop off an A here. So 4 is tetra, O is oxygen, oxygen becomes oxide, so tetraoxide. Notice we leave off the A because we don't want an A and O there, so we drop the A, and so it's just tetroxide, and so we don't have the two vowels there. All right, so for this next one, N2O5, so the prefix for 2 is di. There's 2 nitrogen atoms, so it's going to be, let's see here, N2O5, so dinitrogen. 5, the prefix for 5 is penta. Penta and then oxygen becomes oxide. Again, we have this AO issue, so it's just going to be pent oxide. Okay, so dinitrogen pentoxide. Okay, dinitrogen pentoxide. All right, next one, BCl3. B is boron, Cl is chlorine, 3 is tri, so boron tri, chlorine becomes chloride, so boron trichloride. All right, SF6. So looking at SF6, so S is sulfur. There's only one, so I don't need a prefix there. The prefix for 6 is hexa. Okay, fluorine becomes fluoride. So sulfur hexafluoride. Next one, PF5. P is phosphorus. Fluorine becomes fluoride. There's a 5 there. That means the prefix for 5 is penta, so it's going to be phosphorus pentafluoride. Next one, P4O10. So 4 is tetra. So it's going to be tetraphosphorus. 10 is deca. Oxygen becomes oxide. So penta or tetraphosphorus deca oxide. And then here we have P2O10. So here we have the prefix for 2, which is di, and then P is phosphorus. And then 10 is deca, and then oxygen becomes oxide. Okay, so P2O10, diphosphorus deca oxide. All right, so let's go back and try to name, or try to write the formulas given the names. All right, which we haven't really done, and so I'm going to do a little side note here because it's not showing you some examples. Probably they have some in the back of the chapter. So let me just make some up really quick. All right, so if I have trisulfur dioxide, all right. So what's nice about having to write the formula, if the compound is molecular, it tells you how many you have to have. So remember whenever we were writing the formulas for ionic compounds and we had to do the math to figure out how many there were for each? Remember, like we had sodium chloride, we were like, we don't know what the subscripts are here. We have to figure them out by knowing the charges on each ion. Well, with molecular compounds, it's not that difficult because the prefixes tell you what, how many there are. So isn't that nice? So tri is a prefix for 3. Di is a prefix for 2. Okay, so what this is telling me is I have 3 sulfurs. So symbol for sulfur is S, capital S. And then so it's going to be S3. And then I have 2 oxygens. So 2 oxygens. So the formula would be S3O2. All right, let's do another one. Tetracarbon. Decahydride. All right, so tetra means what? There's 4, right? It's a prefix for 4. So it's telling me it has 4 carbon atoms. Deca is a prefix for 10. Hydride is from hydrogen. Okay, this is a hydrocarbon here. So I have 10 atoms of hydrogen. So the formula would be C4H10. So trinitrogen monoxide. All right, so tri is 3. So there's 3 nitrogen atoms there. monoxide, mono is 1, oxide comes from oxygen, so N3O would be the formula for trinitrogen monoxide. All right, so again, these are really simple. The prefixes tell you how many atoms you have for each element, so hopefully that's not going to be an issue for you when you're trying to write the formulas if they give you the name. All right, so another type of compound that you need to know how to name, they're called hydrates. Okay, so what is a hydrate? It's a compound. It's often ionic, and oops, don't know what's going on here. Sorry. And it has it contains one or more water molecules bound within the crystals. Hydrates are kind of neat because when you have them in a bottle, sometimes the water escapes, and so you have little water droplets in the container that it's in. So hydrates are can be dehydrated by removing the bound waters, yielding an anhydrous compound. To name the hydrates, you name the anhydrous compound as usual, based off the rules that you already know for ionic compounds. Then you're going to add the word hydrate with a Greek prefix denoting the number of water molecules. All right, so formulas for hydrates are written with by appending the formula for water to the formula for the anhydrous compound, including a stoichiometric coefficient denoting the number of water molecules and separated by a variety or vertically centered dot. Okay, so here are some examples. So we have copper 2 sulfate. Okay, so you would name this just like you normally would. Of course, copper is a transition metal, so you have to have the Roman numeral 2 indicating the charge on the copper atom. And then sulfate is a polyatomic ion, SO4. And then they talked about vertically centered dot. This is it here. Okay, that means that these 5 water molecules are complex with this every copper 2 sulfate molecule. And so this the name of this would be copper 2 sulfate. 5 is the prefix for 5 is penta, so penta hydrate, right? Because it has hydrate means that it has water molecules complex with whatever the ionic compound happens to be. In this case, it's copper 2 sulfate. All right, the next example here, calcium chloride monohydrate. So calcium is not a transition metal. We don't need a Roman numeral here. So it's calcium chloride, and then we see that there's 1 molecule of water, so it's mono is going to be the prefix for that, and so calcium chloride monohydrate would be the name for the second example. All right, so let's look at some examples in your text. All right, so we started doing some of these problems and here, and I stopped because we didn't talk about hydrates yet. So now we're at the point where we can actually name part D. So it's MgSO4.7H2O. All right, so if we look at our formula here, we're going to name this ionic compound just like we normally would. Okay, so if we look up magnesium on our periodic table, we notice that magnesium, it's a metal. It's not a transition metal. So what does that mean? It means that we don't have to have the Roman numeral, right? It has a single charge. So the cation name for MgSO4, Mg is going to be just magnesium. Okay, and then SO4 is a polyatomic ion. That's called sulfate. Right, SO4 sulfate. So magnesium sulfate, and then the dot here just represents it complex together. The prefix for 7 is hepta, right? So this is going to be magnesium sulfate, hepta, and then the word hydrate, heptahydrate. Okay, magnesium sulfate, heptahydrate. That would be the name for this formula here. All right, and then finally, the last example here, example E. We have Ti2SO4-3. So if we look up Ti, so Ti is titanium, is a transition metal, so that means we need to have a Roman numeral in there somewhere. So now we need to figure out the charge on the formula first, on the sulfate part of it. So here's sulfate. We know the charge for sulfate is 2 minus per sulfate ion, okay, and so there's 3 of them. So 3 times 2 is negative 2 is negative 6. So titanium must have a positive 6 charge overall, right? But because there's 2 here, for each atom of titanium, it's going to be 6 divided by 2, which is 3. So each titanium atom is going to be positive 3. So here, this formula is going to be titanium, its name, and then positive 3, so it's Roman numeral 3, right? And then sulfate, titanium 3 sulfate.